I will call it. Da da da. The deep voice comes out. Thank you. Hi. Welcome back. I hope you enjoyed the discussion of drag last time. I enjoyed doing it, and I hope you learned something from it. We're done with that right now, but I do think you should revisit it. I've given you a solution. I've given you, you can plot it, you can do whatever you want with it, okay? Today, I want to discuss how we measure the length of a curve. How we measure the length of a curve. So, well, I'm going to do three things. I'm going to discuss the procedure for measuring the length of the curve. That'll lead us into a discussion of a different parameterization of a curve. Instead of the parameter we use is t, we'll use a different parameterization, which will be the arc length parameterization. And I'm going to discuss how this is a natural parameterization, the kind of intrinsic parameterization for a curve, okay? And then ideally, either today or Wednesday, we will get into line integrals. And on Wednesday, we will finish curvature. And we will be done with chapter 13 after Wednesday, because we've got to go into chapter 16. Okay, chapter 16 is a lot of stuff. So I'm going to tell you, there's no class on Friday, apparently. Right, everybody's, yeah, sure, yeah, no class, yeah. There's no class Wednesday either. No, there's no class this Friday in celebration of Veterans Day. So this will be the last for chapter 13. And so I'm going to insist that you read chapter 16. And I really insist that your homework for Friday, for Thursday, Friday, Saturday, Sunday, is to begin reading chapter 16 as far as you can get. Read it, okay? Chapter 16 is the first difficult material we will encounter. Okay? I'm saying that everything up till now has not been difficult. This is actually now difficult material. And it is also the apex of calculus, okay? Where we are going to develop Stokes' theorem. Yeah, that's a bit of I'm trying to concern you a little bit, right? I'm trying to help you prepare yourself by giving you a little bit of fear, a healthy fear, which you're going to confront by attacking it, not by running away from it, okay? So that's where I want you to be for this weekend, but right now we're going to do a curve, okay? I'm going to do a curve. So what's the curve? If you were to estimate the length of this curve, what would I do? Well, I can measure a straight line, and so I can measure this eraser, and I think this eraser is probably 30 centimeters. It reminds me of my rulers when I was a kid in elementary school, right? It's about the length of a ruler. So then I would say, hey, this curve is 30 centimeters. So this piece of the curve is about 30 centimeters. I'm going to estimate it from there to there that it's 30 centimeters, okay? So I'll do that, and then I'll estimate it from there to there that it's 30 centimeters. So I'll do that, and then I'll estimate it from there to there that it's 30 centimeters. So I'll do that, and then I'm going to try to estimate, I'm a sloppy. I'll call that 30 centimeters. And maybe that is, I'll call that, say, 30 centimeters from there to there. And of course, I'll do that from there to there is 30 centimeters. So notice what I'm doing each time. And from here to here, 30 centimeters. Goodness gracious, I got lucky. So that was 1, 2, 3, 4, 5, 6, 7. That is 7 times 30 centimeters, 210 centimeters. So 2 meters and 10 centimeters, okay? 210, okay? Now, critique. You criticize me, right? You should criticize me. Am I exactly right? Okay, so what have I missed? Is it too obvious? These are rhetorical questions, right? The answer is too obvious to ask you, so it's an insult. I mean to ask you in a rhetorical sense, right? What have I missed? As it was pretty ridiculously obvious that this length right here, the length of the curve, is significantly larger than this 30 centimeters because of the wiggle, right? It was pretty clear even over here, right? That's bowed out. That thing's got to be larger than 30 centimeters, okay? So I didn't do a good job. I missed it, okay? In lieu of using this big ruler, I'm going to say here's a piece of chalk that's 1, 2, 3, 4 times. It's a quarter of 30 centimeters. So it's 7.5 centimeters. Please remember that, front row. 7.5 centimeters. And so I'm going to now measure this with the smaller chalk, 7.5, 7.5, 7.5. Oh, my God. That wasn't supposed to happen that way. It wasn't supposed to happen that way. Why did it work that way? What did I do wrong? Well, measurement error. I made too much measurement error, and I just broke the chalk. Anyway, the point is, if I measured it with a smaller ruler from end to end, the error I would make on each piece would be less. Okay, that's what I'm trying to show you. In effect, I'm trying to show you that the estimate of the length from here to here by this blue thing does make an error, but that error is significantly smaller than the total error that I made with the ruler. Therefore, by measuring with the blue, I'm getting a better estimate for the length from here to here than I would with the long eraser. Okay? You guys want to tell me something? You guys are thinking over there, or are you just laughing? No, that's okay. I thought you had something. That's obvious, right? Yeah, that's what we're doing, right? I'm trying to emphasize that that's pretty much all we do, right? All the time, all I ever do is chop things up into pieces, right? Measure the piece that I can measure, recognize that I've made an error, but in the limit that that error goes to 0. Okay? Exactly. So I won't be long-winded. Second row tells me stop being long-winded. I can handle that. So I'll move forward and say we have to measure the length of these curves. How do you do it? Well, if you literally physically had a curve, you would literally be doing what I did right now, which is literally taking a ruler of small size and putting it end to end and walking along it and recognizing that you made some error. In fact, the way to do it would be with a couple of rulers, a longer one and a smaller one, and then see how the error changes between how the difference in the sizes that you measure change between using those two rulers, and then get an estimate of where that would converge in the limit. You could sort of eyeball the limit. Whether you like that or not, that's what you would do. But what we are really considering is curves R of t, where we have a parameterization, x of t I hat plus y of t j hat plus z of t k hat. And now, if I were to take a piece of this curve, allow me to take, I don't know, say this piece from here to here. There it is right there, bada bing, okay? There's that piece of the curve, and I want to measure just that piece. If I know how to measure this piece, I know how to measure the whole thing. Okay? So let me say that there's a coordinate system here, and that curve is given by r of t, so that this is r of t0, and this is r of t1. Then from your 21c, you understand that this vector right here is r of t1 minus r of t0. That's that vector. That's this vector right here. And I'll call that vector delta. In fact, I'm going to call that delta S, if you don't mind. Okay? In fact, I'm going to call it delta S at t0. Just because I feel like it. Okay? This is a vector delta S at t0. What is that vector? Well, that's the vector that connects the first point on this segment of the curve to the last point on this segment of the curve. What are the units of that vector? That vector has units of a length. Okay? What is the length of that vector? The length of that vector is the length of this straight line. So the modulus of delta S vector is equal to, I'm going to call that delta S. That's the length of that straight line. That straight line is approximately equal to the arc length of the curve. How does it when would it equal the arc length of the curve that you're thinking about? Well, if I was at another time that was closer or another time that was even closer, you recognize that as you zoom in to that curve, and I'm going to go over here now, as you zoom into that curve, here is r of t, 0, and here is a later r of t, okay, r of t1, or maybe I'll say, I'm going to call this r of t0 plus delta t, slightly farther away. I'm trying to zoom in, so I can't see, since I'm zooming in on just that circled part, I can't see where these guys make it to the origin, where the origin is way down on the left. So there's a segment of the curve there, and oops, I shouldn't have circled it because now it's getting too busy. But that straight line from the two ends of those two arrows which is delta S vector, the magnitude of that is approximately equal to the length of the curve, the length of the curve between them. And in the limit, I hope you can see as I zoom in farther and farther, the amount of arc that I get is less and less. Okay? So this gives us a formula. Actually, now I can write this formula. Length of a curve is equal to the sum I equals 1 to n of all the delta si's, where delta si are each of the individual pieces. That would have been delta S0, then you have delta S1 and delta S2. And then you have to take the limit that the maximum delta S goes to 0. And notice what you're doing here is when you're not taking the limit, this is the sum of a bunch of lengths. And when you take the limit that the biggest delta S goes to 0, what you're doing is taking all of these are going to 0, and of course n is going to infinity because you're keeping your endpoints fixed. That's exactly the balance that you get in an integral. Every term in the integral gets smaller, but you get more and more and more and more and more in terms as the limit that they go to infinity. Infinitesimal, infinite number. Okay. Well, that's fine and dandy. Now how do we compute with this? How do we compute with it? Okay? And the way to compute with it is actually really straightforward. Okay? What we recognize is that this is the limit as the max delta S goes to 0 of the sum I equals 1 to n. And we do a simple multiplication. We multiply by 1, a form of 1. And the form of 1 is simply delta t in the numerator and delta t in the denominator. Why? Well, the curve is parameterized by t. Okay? And we know that if you take smaller and smaller amounts of time transpiring from your first measurement point to the second measurement point, your delta S, the distance you've traveled, is going to be less and less. Right? If I strobe every second versus if I strobe every minute is longer than every second. So in the limit that delta t goes to 0, this term will go to 0, but this ratio will not. Okay? So length is equal to the limit that max delta S goes to 0 of the sum I equals 1 to n. Now, delta Si is the magnitude of vector delta S. So this is the magnitude of vector delta S vector. And I can put the magnitude on the bottom, too, like this. Because delta t is going to be positive. My t is going forward, so the absolute value of delta t is equal to delta t. Now, this thing in the numerator is just, this is delta Si. I apologize. This was delta Si. There should be an I to tell you each successive one. Well, this is going to be R of Ti plus delta t minus R of Ti divided by delta t, all in absolute value, multiplied by delta t. That's what I define this, right? Delta Si is the next one minus this one. Okay? But in absolute value. So absolute value for a vector means Pythagoras' theorem, right? You have to do each component squared, square rooted. Well, folks, in the limit that delta t goes to 0, this thing is the definition of the derivative. This is the definition. This is the derivative. And so this is the limit max delta. Now we don't have to do max delta S. We can do delta t goes to 0 because we don't have delta S there anymore. I equals 1 to n of the magnitude of dr dt dt. And in the limit, this you see now, this is just a function of t. So what you have staring at you is the integral. This is the definition of the integral in one dimension. This is an integral in 1D. Good old 21b integral. This is the integral from t0 to t end. Maybe I'll say t begin to t end, from wherever your curve starts to wherever your curve ends, of the magnitude of dr dt integrated with respect to t. That's how you calculate the length of the curve as an integral. And just to say this in words, dr dt is the velocity, the magnitude of the velocity, gets rid of the direction, but keeps the units, right? So the magnitude of dr dt is the speed, is what we call the speed. But the speed is changing along the curve. So this is the integral of the speed with respect to time, which is the total length, which is what you would have understood when you were in high school as the total length. Okay? This expression is the expression in general for any general curve. What's the issue with this expression? Well, like I said, let me write it in t begin to t end. Let me write it in components. This is dx dt quantity squared plus dy dt quantity squared plus dz dt quantity squared, all to the power of 1/2 integrated with respect to time. So you have these three functions. The assumption is you have x of t, y of t, and z of t, because you have r of t. So you have these three functions. All it says, take their time derivative, square them and add them together, and then take the square root. Now, just think about, though, having to do this integral by hand, right? It's not a nice integral for almost any curve. For almost any curve, this is a not nice integral. Except for two curves that it's really, really nice. For the line, it's nice. And for the circle, it's nice. But we've already studied lines and circles. So I don't want to do it for a line and a circle. I want to do it for a line plus a circle. And that's called a helix. So for a helix, it's nice also. So let's do it for a helix. And in that way, I get to have an excuse to teach you about all sorts of the angles that appear in the helix. We'll learn about the length of the helix. And we will also ideally understand arc length parameterization pretty well. Okay? So line plus circle. So for the biologists, obviously this comes up a lot because of DNA. For the people in mechanics, physicists, this actually comes up a lot because a spring is a helix. So we're going to understand all of that. Okay? So consider a circle in the xy plane of radius r plus a line going up in z to a height h, capital H. Okay? So let me draw the picture I have in my head. This is going to be x, this is going to be y, this is going to be z, and I'm going to start on the x-axis at a distance capital R away from the origin. That's going to be the radius of this circle. So from above, the helix looks like a circle. Okay? And then it's going to spiral up around. I stink at drawing these things. Now, even after so many years, he can't draw it to his own satisfaction. La 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 la. You guys know what a helix looks like. Why am I flailing today? I can't do it today. I really can't do it today. It's too bad because it's the one day I'm getting recorded. I've done it before. Claire, you saw me do it before. It came out great that time. This one should get bigger? Say that again. I didn't hear the funny part. Ah, it's a helix. It's a spring. I'm just choking. When you choke, right? It doesn't matter. Like my brain is now totally choked. You guys have had that happen. This is looking on the x-axis. It looks like this. There you go. Thanks. We'll do it that way, okay? And then from above, it looks like that. Okay? Sorry. Okay. The point is, it goes around once in the xy plane, and it goes up to h. I need to parameterize this thing. Okay? So first thing is, what is the r of t of this simple circle? Well, it's x of t, y of t, etc. I'm going to make it counterclockwise, so we have the cosines and the sines just fine. Okay? So it's going to be r times the cosine of. I like to think of t as a time. You cannot pass time alone as an argument to cosine or sine. It must be a dimensionless thing. So what I'm going to say is it's going to be 2 pi t divided by capital T, I hat. Capital T is a number. It's the period. It's the t that it takes for that curve to make it back around. When little t is equal to capital T, cosine goes from 0 at t equals 0 all the way to, cosine goes from 1 at t equals 0 all the way back to 1. So it executes one period. That's called the period. Okay? So this is the period. Plus r times the sine of 2 pi little t over capital T j hat. That is the circle. But to that, I have to add a line that goes straight up. Okay? So the line, it's going to start at z equals 0, and the circle is going to start at x equals r, and y equals 0, and z equals 0. Well, the helix will start at x equals r, y equals 0, z equals 0. So you'll start at z equals 0, and then when you've gone around once, which means you've gone to a time capital T, I want it to be at z equals h. Comes up and back up to h, okay? So if you think about that, this is going to be t over capital T, because when t is 0, whatever is going to be here is going to be 0. And when t is capital T, this whole thing has to equal h. Okay? And so this is a very simple line that goes straight up. Okay? So this, I claim, is the helix. Now, what do we know about curves in general? I can take the time derivative of this, dr dt. Let me take dr dt. And that's easy. I get a 2 pi over t out front of each of these. And so that's going to be 2 pi r over capital T. Recognize that 2 pi r is the circumference. Minus, I'm going to have the sine of 2 pi t over capital T I hat. Put that in parentheses. That's this. Plus the cosine of 2 pi t over capital T j hat. That's just this term and that term. Plus the time derivative of the k hat component. So I want you to stare at this expression for a second because there's a lot going on here. Okay? Think about the helix. This is the tangent vector to the helix, right? If I were to divide it by its magnitude, which would make it a little busy, I'm not going to do that division, but if I were to divide it by its magnitude, that would truly give you the tangent vector. Actually, maybe I will do that division. It's busy, but it's not so busy. Let's see what we get. Well, I'm not going to divide it by its magnitude. It's going to be too complicated. It'll just be a lot of algebra, and you'll hate the algebra, okay? But what's happening with this helix? It's the tangent vector. Let's imagine evaluating this tangent vector at time t equals 0. Evaluate at time t equals 0. What happens at t equals 0? Well, at t equals 0, this part is 0, and this part is 1. Okay? So Let's write it out. At t equals 0, dr dt is equal to 2 pi r over capital T times j hat, that's the j hat term, okay, plus h over capital T k hat. That's the k hat term. And what's the magnitude of this? Only at time t equals 0. We're evaluating the magnitude at time t equals 0. Well, that's equal to the square root of 2 pi r quantity squared plus h squared. That's this squared plus this squared. And of course, I have to divide by the t. It's squared and square rooted. Okay? I just took this squared plus this squared. That's what you get. And if I were to do the unit tangent, so this is a tangent vector. The unit tangent is dr dt divided by the magnitude of dr dt. That's what we mean by a unit vector. We notice that the capital T's cancel out. They don't, the unit tangent doesn't care about this capital T. And you're left with 2 pi r over 2 pi r squared plus h squared, square rooted, j hat, plus h over the square root of the same thing, k hat. You all see that? But remember, this is a unit vector. This is a unit vector. So let's just plot this vector in the yz plane, right? In the yz plane, this vector has a run of 2 pi r over this hypotenuse, and it has a rise of h over this hypotenuse. So the run here is 2 pi r, and the rise is h. And so, what have you just created here? You've got this angle here. I'm going to call that alpha. Sorry that I'm drawing it so small for you guys at the back. That's alpha. That's the pitch angle. So imagine this is like an airplane taking off just for a moment. You rise at an angle alpha. How is that angle determined? It is the total height you go up divided by the total horizontal distance, which is the circumference of this circle. This is the pitch angle. And so you can see really quickly from this expression, or just taking the division, that alpha, the tangent of alpha, is h over 2 pi r. So that tells you that this tangent vector encodes angles. So if you want to know the angle, the direction that you're traveling in this case, you're pointing up. That's given by alpha. Why did I do it at t equals 0? Because at t equals 0, you're definitely going in the yz direction. But of course, that's turning around as you ascend. So it gets a little harder, but you're still maintaining that vertical pitch. Okay? Well, what's the length of this curve? Let's see the length of this curve now. So I have to implement this expression where length is equal to the integral from the beginning to the end of this square root. So let's try it. I need to calculate the magnitude of dr dt everywhere. So there's dr dt as a function of time. What's its magnitude? So that was the magnitude only at the initial time. The magnitude of dr dt for all time is generally a function of time, but it's going to be 2 pi r over t quantity squared times the cosine squared of 2 pi t over capital T. That's the first term. No, sorry, the first term was sine squared. That's the first term. The second term is 2 pi r over t quantity squared times the cosine squared of 2 pi t over capital T. That's the second term. Plus h squared over t squared. That's the third term. And notice this factor is common to the sine squared and the cos squared. And so you can factor it, and sine squared plus cos squared equals 1. So this is going to be, and by the way, I should take the square root of this whole thing, because that's the magnitude is the square root of that. This is going to be equal to the square root of 2 pi r over t quantity squared, that's from these two terms, plus h squared over t squared. That's the RDT. And now, hopefully, you see why I used a helix. Because in this parameterization of the helix, for a regular, nice, steady helix, and this is literally what a plane would do in a holding pattern, or a spring does it, or DNA, at least one of the strands of DNA does it. So it's kind of a ubiquitous shape. It's a useful shape. What's great about it is dRdt is constant. Is that good? dRdt is constant. So the length of one turn, let's just do one turn of the helix, okay? If you know how to do one turn, you can do 2 turns. You just multiply by 2. Okay? Length of one turn of the helix is equal to the integral from time t equals 0 to the period, capital T, of that expression. But look at that expression, by the way. Capital T is common to the denominator of that expression. So this is 2 pi r squared plus h squared over capital T integrated with respect to little t. So I just factored that expression. And I would point out to you the magnitude of dRdt at any time is also the magnitude of dRdt at the initial time. This is a curve who's maintaining its speed. It's just changing its direction. Okay, it's just pitching up and turning around. Well, this integral is ridiculously easy because it's constant. So the result is capital T, which cancels this denominator. And it tells you the length of this curve is 2 pi r squared plus h squared. And now it tells you that triangle I drew over there is actually kind of cool. You take a helix. You want to know how long the helix is. You unwind it, and you're like, oh, I had a triangle. I had a triangle whose base was the circumference of the circle that it went around, and whose height was truly the height that it went. Because this is the length of a hypotenuse of a triangle with base circumference of that circle squared plus height squared. So I find this to be a very beautiful expression. Clearly, you guys do not. I don't see the moment of awesomeness here. Fine, I don't care. But I claim for you that this expression actually tells you something else. Okay? Remember those little finger trap toys that we had as kids? Yeah, it was always lots of fun, right? So what happens in the finger trap toy? Let's just think of a spring, because you don't have to go with the finger trap toy, right? To have a spring that you can stick your finger in when it's just relaxed. And now try to pull. Okay? What are you doing when you pull the string? Well, L is fixed because you bought the spring, right? You got a certain length of wire. That's the total length of that wire. You can't change that length, okay? But by pulling, so you've got this guy fixed. By pulling, you're increasing h. And so by necessity, you're decreasing r in this fraction, exactly like this. Exactly like this. Okay? So this doesn't just encode a geometric fact, which it does, okay? A fact about vectors with a pitch angle and all these other things, but it also encodes for you something else, which is, it tells you a physical fact, which when you conserve the length, you have to add, the length is preserved, you must have a trade-off between radius and height. Okay? So that's the helix. I think that's a very, very nice example. I do. Maybe you don't. Okay, so that, I wanted to talk about that. But now this kind of motivates another question. Okay? I think this motivates another question. This motivates a question, why do we use t? Notice that t popped out of this expression. Why do we use t as a parameter? T is not a very natural thing, right? T is how quickly do I traverse this curve? Well, if you had a plane, it's natural. But if you had a spring, I could go fast and slow and fast and slow. This t thing is not a natural way to discuss the curve. What's intrinsic to the curve is actual length, is the actual length. So the example I like to use here very often is to think of yourself on a highway. And since I've been living in Davis long enough, I think of myself driving on I-80. Okay? So let's e.g. a highway. And here's Davis. And here's like Sacramento over here, okay? and that's I-80. Now, on a Friday afternoon, your R of t, right? Maybe you're, well, you can know, on a Friday afternoon, your R of t moves very slowly. Your dr dt is very, very small, right? Because you got lots of traffic going into SEC. So if you were to tell me, I will be in the middle of the causeway, there's a causeway over here for those of you guys who haven't driven it. I will be in the middle of the causeway at 5 o'clock, because I left Davis at 4 o'clock. Well, it might not be true on a Friday afternoon. But on a Saturday morning at 6 a.m., if you left Davis at 4 o'clock, you would be in the middle of the causeway at 4:05. So telling me the time that you'll be there is not the best way to tell me where you will be. But if you tell me the mile marker you're at, that's a useful way to tell me where you are. So the point is, what we have that's natural to the curve, 1 mile, 2 mile, 3 mile, 4 mile, 5 miles, 6 mile, it's not 7 miles, it's not 8 miles, this is West Sac or something like that, 8 miles, okay? What's intrinsic to the curve, and what you see on the side of the highway every time you drive, is a mile marker. And the mile marker provides exactly what is called the arc length parameterization. And what that says is, if you tell me that you're at mile 5, I will know exactly where you are. If you're telling me it's 5 minutes after 4 o'clock, I have to know how you've been driving to know where you are. Okay? So the arc length parameterization is natural to the curve. Okay? So how do we construct an arc length parameterization? So the arc length parameterization rests on this definition, and it's very straightforward. Okay? We use S, because I've used S already, we use S to denote arc length. And what do I mean by arc length? Well, arc length is a length on a curve, on something that is curvy, therefore an arc. But as distinguished from length, the difference is length is the total length from one end to another end. Full stop. What we think of as arc length is the length as a function of location. Where you are, how far you've gone as a function of location. Okay? And so what we mean, we let S equal the integral from, let's say the beginning point is going to be t0. We always, let's make it 0, just because we're going to make it 0. You have some beginning time. Okay? Now you're going to measure the length of the curve, which I already said is the magnitude of dr dt. And you're going to integrate that with respect to t. Now, allow me this, everybody. I'm going to emphasize that dr dt is a function of time. And I'm going to use the dummy variable t prime. This is not derivative. This is not derivative. It's just a dummy variable associated with t. dr dt, evaluate t prime, integrated with respect to t prime. And I integrate this from 0 to some fixed, so some general later time t. Before, I chose capital T to represent one turn around the curve. This is any time t. So if you take a look at this expression, you say, oh, I have this function of t. I evaluated the dummy variable, integrate with respect to the dummy variable from 0 to a general later time. Therefore, this arc length must be a function of time. Okay? So let's see what that would mean for the previous expression. If I go to this previous expression here, everything inside the integral remains the same. The only thing that changes is the upper bound. Instead of capital T, you have little t. Okay? So this says for the helix, e.g. helix, S of t is equal to, it's equal to this whole length, 2 pi r squared plus h squared times little t divided by capital T. So this is the amount of distance you've traveled in a time t. Okay? But think of it, it's pretty straightforward. If little t is 0, this whole expression is 0, and you haven't traveled anywhere. If little t is big T, you've traveled the whole length of one turn of the helix. If little t is a quarter of big T, you've traveled a quarter of that length. It's really straightforward. Now, for most curves, it doesn't come out this straightforward. This is a linear function, right? It's because of the steadiness of this whole problem. That's why I'm doing this problem. For most curves, it gets a little more complicated, okay? But now, look what we've got here. I have the parameter t, which is the parameter that I chose. But now I have calculated the distance traveled at any t. So distance and time are related to one another. At 5 seconds, I've gone a certain distance. At 10 seconds, I've gone a certain distance. Or I could put it differently. I could remove little t in favor of s. Okay? This is not just a relationship s of t. I can write t of s. I can invert that relationship. So let me invert that relationship. I will do it over here, and then I will use this board again in a second. Please allow me to call this square root L, okay? Just so I don't have to keep rewriting it. L is equal to the square root of 2 pi r squared plus h squared. That's the length of one turn of the helix. Now, if I write it that way, for the helix, for this helix, this simply parametrized helix, it's really simple. You have S divided by L is equal to T divided by T. It's because it's a simple shape. It's the circle and the line that it comes out this nicely, and in general, it's not going to come out this nicely. Put differently, T is equal to capital T times S over L. So I think of this as T of S, the time at which you achieve a certain distance along the curve. That first thing was the distance you traveled after a certain amount of time. This is the time at which you achieve a certain distance. Okay? That's what the inverse function tells you. Now, instead of writing r of t, I can get rid of little t by making that substitution in there. Okay? So let's do that substitution. R of t of s is a function of s. This is composition of functions. Okay? So this is going to be some other function, r of s. And let me call it, I need to give it a different name because it's a different function of s, right? It's not the same function. You can't just call this r of s, right? So I'm going to call this capital R vector of s. That is the arc length parameterization of this curve, where s is the arc length. And so wherever I see t in that expression, I substitute that. And now you see that it's very simple. You've got capital R times the cosine of 2 pi s over L I hat plus the sine of 2 pi s over L j hat plus h times s over L k hat. And that's the arc length parameterization of this curve. Now, it's pretty easy. It's pretty easy, I think. It's a pretty easy parameterization. Okay? It happens to be this easy because it's the helix, because of the circle and the line property of it all. But now I have an expression r of s. Okay? In the book, by the way, they will write this as little r of s. They will write this as little r of s. I think it's a little bit imprecise, because this says take the time parameterization and replace t with s. And you can't replace t with s. You have to replace t with capital T over L times s. So that's the arc length parameterization. So you have to be careful about understanding this. But let's just say, let's use the book's notation. And now I have a function r of s. What is the derivative of that function with respect to s? Let's consider the derivative. Consider dr ds. What are the dimensions of this thing going to be? The units. The numerator has units of meters, and the denominator has units of. So it's going to have no units. Meters divided by meters. Scratch, 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 scratch. Interesting. Let's do it. So we got 2 pi r over L. It would be capital R, but like I said, in the book, they definitely use little r in lieu of capital R. So I would write it like this, but I've noticed in the book they write it little r of s, okay, as the arc length parameterization. So let's stay with the book's notation. I gave this little, this is more precise in terms of composition of functions, okay? Because the function you get as a function of s is different than the function you got as a function of t. So I have 2 pi r over L times negative sine of 2 pi s over L I hat plus cosine of 2 pi s over L j hat plus the derivative of that with respect to, the derivative of the last term with respect to s is easy. That's just h over L k hat. Well, that's just a vector, right? But that's parallel to the tangent vector. Right? It's got to be parallel to the tangent vector because it's just another parameterization of the curve. Right? So this is parallel to t hat. It's parallel to t hat. I know it has no units. I know it's parallel to t hat. Let me do one more thing. Let me calculate the magnitude of dr ds. The magnitude of dr ds is this term squared plus this term squared plus that term squared. Well, this term squared is 2 pi r over L quantity squared, right? Because sine squared plus cos squared is 1. That term squared is h squared over L squared, all to the 1/2. And this is 2 pi r quantity squared plus h squared, all divided by L squared to the power of 1/2, which is equal to 1. Because that is L squared. That numerator is L squared. In other words, this is a vector which has no dimensions. It's parallel to t hat, and its magnitude is 1. Therefore, it is t hat. Therefore, another expression for t hat is dr ds is equal to t hat. This is the arc length parameterization of the tangent vector. And I want you to say this in words. The derivative of the position with respect to distance traveled, the derivative of position with respect to distance traveled is the unit tangent vector. Your unit tangent is how much position you change, which is a vector position, compared to how much distance you travel to change that position. Okay? So that is the whole idea of length of curve and arc length parameterization. I don't have time to start line integrals right now. I don't know where I'm going to start line integrals. I'm going to have to do line integrals on Wednesday. But this geometry here sets up the question. And I'm just going to tell you what the question is here. Okay? When you're turning in a curve, right, your tangent vector, just like imagine it. It sweeps across the room. I'm pointing at you, Mario, and then I'm pointing over here. How much distance do I have to subtend? How much distance do I have to travel to turn a full 2 pi around? If I have to travel a very little distance, I'm traveling on a very little curve, on a very curvy curve, a high curvature curve. If I'm traveling a very great distance, I'm traveling on a very low curvature curve. So it's going to be the derivative of this tangent vector, again, with respect to arc length. The derivative of this thing with respect to s is going to give me the curvature of the curve. So since I've given you this expression right here, it's not so hard to take its derivative with respect to s in the next step. So go ahead and do that. And you're going to get a vector again. And the magnitude of that vector is the curvature of this curve. Okay? So that's what I'm going to finish up on Wednesday, and then we're going to do line integrals. Okay? No class on Friday. Quiz tomorrow, I think what I said was on spherical coordinates. Okay? Huh? never invertible functions.